Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the University of Helsinki in Finland in the Helsinki Institute of Physics over the University of Helsinki in Finland. Messed up my intro again. Welcome to Cup of Cosmology. This is the place for all your questions about the universe. The idea here is that this is an interactive stream. I can't believe it's been so long since I've been live on Cup of Cosmology that my intro's all over the place. Anyway, if you're a first-time viewer, welcome. If you're a regular, welcome back. It's great to see everybody here. I see some of the regulars coming in. Paul, Scott, great to see you. Anna, great to see you as well. Don't see you often in the comments. Prath, great to see you. Nina, so nice to see you live. Finally caught me live. I know you've been leaving a lot of comments. Great to see you here live. So, hello everybody, I'm a theoretical physicist. I study cosmology, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, basically all of the fun stuff happening inside the universe. It's a great topic. I love being a cosmologist, I love being a scientist, I love getting to research some of the cool stuff happening inside the universe, and I love chatting to everybody about all of the cool things happening in the universe. So, yeah, I'm a theoretical physicist, I study the universe, and I love chatting to people, and that's the purpose of the stream. The idea here is that this is an interactive stream, so you people can ask me anything you want about cosmology, about science, about physics, about academia, about life in Finland, whatever you want, and I will do my best to answer your questions. Now, I don't have all of the answers, of course, but I will try to answer the questions that I do know the answers to, which, depending on the week, is a lot or not much, because some weeks you will ask me very tough questions, and some weeks you ask me questions that I do know the answer to, and all of them are equally fun, and I love it when you all stump me with questions. If you're new here, please do click the subscribe button. If you're a regular and you haven't clicked the subscribe button, please do that as well. Leave a comment, like, do all of the usual YouTube things. So I'm going to start with a few announcements and then get into everything. So hello to everyone joining. If there's anyone I missed in the comments, sorry, a bunch of you said hello at the same time. Great to see everybody here in the comments. And yes, Happy New Year to everybody. It is the first time I'm online this year. There's been a lot going on. I was last online middle of December. And then I traveled to India for a week, so I missed the stream because I was in India, which was an absolutely amazing experience. I was in India for a wedding; it was amazing. Then I got back, and the day after getting back, I tested positive for COVID, and that wiped me out for the last 3 weeks. Basically, my symptoms only lasted like a week, a few days, but I still got tired very easily, and I'm still out of breath easily. So we're gonna have to see how today works. Last week I didn't do it because there's no way I could talk for an hour. We have to see how today works. There's a chance that I might run out of breath halfway through or start coughing because that's still happening. And if that happens, we'll just wrap it down and end the stream. But let's see how far we can go. Scott, you were complaining that it's cold there. It's probably colder by you. We had a week of about minus 25 degrees in Helsinki. It was amazing. It was really fun. Probably not the best conditions right after COVID because my lungs were not good with the cold. But now it's nice and warm. It's only minus 10 outside, so it's nice and tropical. So yeah, a bit cold here. We have about 30 centimeters of snow. It's spectacularly pretty outside. I love it. If the answer to life and the meaning of everything is 42, what is the question? I think if I knew that would be good, right? Knowing the answer to that one. And I see someone already commented on the sweatshirt. So of course I have to show off this absolutely awesome jumper. I have a space jumper. And it is an awesome space jumper, and I love the space jumper, and it was a second-hand space jumper. So that makes it even better. I love second-hand clothes, and finding a second-hand space jumper is amazing. And I wear it now every time I give a talk, and then I'm like, hey, I'm a physicist. This is what I work on. It's very cool. Okay, so one big announcement to everybody watching on Twitter, or X as it's known these days. Since Cup of Cosmology started back in 2015, so 8.5 years ago by now, wow, every single episode of Cup of Cosmology has also been on Twitter. When I was in the Periscope days, it was going out to Twitter. When I was in the Haps days, it went out to Twitter. And in the YouTube/Restream days, it's been going out to Twitter. As I mentioned, my voice is still, or my coughing is still an issue. So there's going to be a lot of coughing today. Sorry about that. Okay, let's see how long the stream can go on, because I'm 5 minutes in and I'm already coughing, so that is not a good sign. But let's go for this. So, as I was saying, since the early days, Cup of Cosmology has been on Twitter. However, it's now at the point, and I've been warning you all about this for some time now, it's now at the point where I cannot stand by what is happening on Twitter quietly. Therefore, this is the last stream of Cup of Cosmology that will be on Twitter as well. Going forward, all streams will only be on YouTube. So if you're still watching me on Twitter or on X, whatever you want to call it, now's the time to make the jump over to YouTube, because as of next week, this will only be on YouTube. So after 8.5 years, my streams are going to stop appearing on Twitter. Anyone who still tries to contact me on Twitter, don't bother. I'm not there anymore. So you're welcome. You're very welcome to follow me on Mastodon. My username is dchooper91_Cosmo. You can find me there. Any updates about Cup of Cosmology, go out to Mastodon. You should do that. You should also subscribe to YouTube, turn on ring the notification bell, and then you'll get a reminder 30 minutes before I go live telling you Cup of Cosmology is about to go live in 30 minutes. Make sure you do that. You're also welcome to reach out to me on contact@cupofcosmology.com. You're welcome to reach out to me on Mastodon. I have multiple Mastodon accounts, but dchooper91_Cosmo is where you'll get all of the Cup of Cosmology updates. So going forward, this is your last reminder, last warning. I've been announcing this for a while now, but this is the last warning. Next week, do not expect me on Twitter, because Cup of Cosmology is not going to be on Twitter anymore going forward. Follow me on YouTube. At some point, I might resuscitate my Twitch account, but mainly YouTube's the place to find me, YouTube and Mastodon. So, announcement done. Now we can get into physics. And I just see a comment here by Paul about the after effects of COVID can be really annoying for a while. So I actually have long COVID. I got COVID for the first time in April 2020, and I still have effects because of this. So I have long COVID, which sometimes doesn't bother me and sometimes means I basically can't leave the house. So I'd managed to then avoid getting COVID a second time up until a few weeks ago. Getting COVID a second time has, of course, made my long COVID worse, which was to be expected, but quite frustrating. So I very much do feel the thing here that the after effects of COVID can be very annoying. I agree. COVID is very much not just a cold, and it is very much a pandemic still. We very much should be more cautious than we are being. Anyway, let's get into some cool physics. I saw there were already some fun questions. Where were the fun questions? Feel free to ask me anything. This is an Ask Me Anything stream, so you can ask me anything you want. There was a question by David. We have another David in the comments. I think there's now like 3 Davids that join here regularly. That's great. I'd love to see you all. There's a joke in physics that sometimes you go to a conference and there are more people with the name David than there are women at the conference. It's a funny thing that physics conferences have a tendency to be very male-leaning. And you go there sometimes, you go down the list and you find like 5 men with the same name and 4 women or non-men on the list. And it's always an interesting experience. I'm not in any way criticizing people here in the room. It's great to have you all here. I just noticed I'm going to have to start referring to people by surname as well. We'll give you all fun nicknames. That is always fun. Anyway, just comment here from Nina. A good friend got COVID and is still sick half a year later, and it doesn't look like it will ever get better. Yeah, unfortunately, I know a few people in similar situations. Now, personally, I can say that my long COVID has been getting better until I got COVID a second time. So I think it very much varies, and some people are ill for a while and then get better. Some people just deal with long COVID forever. So, yeah, physics girl Diana Cohen has also got a really bad case of long COVID. I followed her for many years on YouTube, and it's quite startling to see how bad hers is. And I think it's an eye-opener for many people who still say that COVID is over. It's very much not. Okay, so the question was, do you have a preference on cosmological theories, inflation, cyclic, so on? I think there's a lot of very, very cool theories and models out there. I think the Big Bang Theory, which tells us the history of the universe from the end of inflation onwards, I think this model is really, really good. And just two disclaimers here. People talk about the Big Bang. It was not actually a bang. Nothing actually banged. So the Big Bang, some people often say like the Big Bang doesn't tell us about the origin of the universe. It doesn't intend to. So the theory of the Big Bang Theory is what describes what happened in the universe from a fraction of a second, so the end of inflation basically, until today. So it takes these 13.82 billion years of cosmic evolution, and it tells you what happened, how different species dominated, at which point you would have radiation dominating, at which point you would have matter dominating, and so on. So I think that's really cool, and it's a model that, so far, it's a theory that we found that best describes our universe. Then there's some issues with the hot Big Bang that you can solve by adding in inflation. For an example, why does the universe look the same in every direction you look? Or why does the universe look the same really everywhere? Why does the universe almost appear flat? And importantly, why does the cosmic microwave background radiation, this amazing thing here, why does this have the same temperature in every direction? So this map that you can see here is a snapshot of the baby universe. This shows you what the universe looked like 380,000 years after the end of inflation. What we're seeing here is the temperature of the photons, so the particles of light, at the time when they broke away from matter and started traveling freely throughout the universe. The blue spots here represent slightly colder, less energetic photons. The orange ones represent slightly warmer, more energetic photons. But the very cool thing here is that these photons are hotter and colder, but these differences are around 1 part in 100,000. It's a ridiculously small difference. So then there's a question of, why are these parts of the universe that are so far apart, why do they have approximately the same temperature? And to answer that question, we can bring in inflation. For anybody keeping track, that was 11 minutes until the CMB appeared today. So last stream, it was only like 3 minutes. So we made it a whole 11 minutes this time. So the hot Big Bang theory cannot explain why the CMB looks the same in every direction. It predicts the CMB, but not why it looks exactly the same in every direction, like this precise temperature. However, with inflation, you get this idea that in the early universe, everything was really close together. And then inflation pushed everything outwards at a dramatic speed. This means that everything we see today at some point in the past was together, and could exchange information and balance out the temperatures. So the question was, what is my favorite theory of the universe? And I'd have to say the hot Big Bang theory, because that's the one that we've been able to confirm, or not really confirm, but it's the one that best describes the universe around us. But it's got some issues, so then you take hot Big Bang and you throw in inflation, and then you can describe the universe around us. So then you can go into a bunch of other theories. Obviously, I think general relativity, which is our theory of gravity, is really cool. But there's a bunch of theories that I also like that may not necessarily be what the universe seems to be, but they're fun, like the Big Bounce. The Big Bounce is this idea that the universe is currently expanding. We know that the universe is expanding, it's getting faster. But the Big Bounce is this idea that at some point it's going to stop expanding and collapse back upon itself. And then you'd have a universe that kind of contracts and then expands and contracts and expands. However, the data doesn't seem to support this. The data seems to show us that the universe is growing, and it's growing faster than it ever was before. So personally, I like the cyclical universe model, but it doesn't really fit the data. So at that point, if it doesn't really fit the data, then we rule it out. That's what you have to do as a scientist. So it doesn't matter how much you like a theory or a model. If the data tells you that it's wrong, then you have to accept that it's wrong and move on. I think the Big Bounce cosmology was a very cool model, but it doesn't fit the data. As fully expected, that is still too hot. I am very bad with my tea. Okay, so yeah. Great question here from Scott. I've seen there's been a few connected questions here. If the Big Bang was hot, how did dark matter get cold? Excellent question. Very cool question. So everything in the universe gradually cools down. Things in the universe used to be a lot hotter than they are now. In fact, when we talk about the history of the universe, we often talk in terms of temperature. When the universe was at 1000 GeV, or when the universe was at 100 Kelvin. And the reason we do this is because these temperatures is what's important for particle connections. Because I forgot to turn off my phone and it's buzzing, so I'm actually just going to close my phone, because else I'm going to get distracted every time it buzzes. There, can't look at the screen now. So the reason we talk about the universe in terms of temperature is because in the early universe, things were hotter, and the temperature kind of tells you what particles could interact. At specific energies or specific temperatures, certain interactions become harder. You no longer have the energy available in the universe to do certain interactions. So we know that the universe used to be a lot hotter than it is now, and everything has cooled down. So we talk about the hot Big Bang because everything it started, not when it started, but when we start talking about particles and the baby universe and dark matter, everything was very, very, very hot. And gradually, as the universe cooled down, interactions stopped happening. At some point, dark matter broke away from everything else. And since then, it's just been kind of cooling down, doing its own thing. The CMB photons, the cosmic microwave background photons, the ones that make up this amazing map, they also broke away from all the other particles. At some point, it was not energetically favorable for the photons to interact with anything else. So they also broke away, and they've been traveling ever since. And if we look at them today, they have quite a low energy. They're in the microwave range of the electromagnetic spectrum, which is quite low energy if you compare them to like gamma rays. When these were produced, they had much higher energy, but they've been gradually traveling throughout the universe. They've been redshifted. So dark matter used to be a lot warmer when it was produced. It used to be, we think, it was probably at some point in balance with the rest of the particles in the universe. So just quick recap here for anyone who's a bit confused, because I'm just assuming a lot of knowledge here. Dark matter is one of the three components of the universe. Everything we see, everything we're accustomed to, everything from me to my tea mug to my phone buzzing, this is normal matter. Normal matter only accounts for 5% of the energy budget of the universe. There's another 25% in the form of dark matter. Dark matter is this type of matter that is pushing the universe. Dark matter is this type of matter that interacts gravitationally but not electromagnetically, so we cannot see dark matter. It is invisible. We know that it's there based on how it gravitationally affects other particles, but we cannot actually see dark matter. And then the remaining 70% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that's everything we know about dark energy. Fun. So dark matter today we describe as being cold, and by cold we mean that it doesn't interact with any other particles. But we think in the very early universe, dark matter actually was interacting with the other particles. They were all very, very hot. They were all bumping into each other. And as the universe cooled down, at some point, the interactions between dark matter and the normal matter became so energetically inefficient that the dark matter just stopped talking to things. And since then, it's not talked to anything since. So it's just sat there getting colder and colder and colder. So even though we talk about the hot Big Bang and things in the early universe being hot, today things are generally very, very cold. Space itself is very, very cold. Today we know that the average temperature of the universe is about 2.73 degrees Kelvin, which is like minus 270 degrees Celsius and minus 440 degrees Fahrenheit. So it's quite cold. But it used to be a lot hotter. So we talk about hot Big Bang, but dark matter is cold now because it's gradually cooled down. I hope that answers your question. And I know there are a bunch of other connected questions, so let's go to that. And I know there was a question by Ben before about stars and black holes. I will come to that one as well. But let's carry on this stream that we're going on now with the universe and stuff like that. And I'll come back to the stars and black hole question. In fact, I'm making a note here, stars, black hole, because then I'll come back to that question later on. But that's also a very fun question. Okay, so when a question from Paul, when the early universe was super dense, would the density get in the way of information sharing from one side to the other? Excellent question. So when we talk about the universe being super dense, what we mean is that everything was condensed in one place. And this actually, in a sense, makes it easier to share information. Because if things are close together, they're in what we call causal contact. So if something here is getting colder, it can spread to everything else. Right? If you think, for an example, if you go out in the snow, which I have a lot of here, let's say I go out in the snow with a water bottle. Now, if I put my water bottle in the snow, this is gradually going to get cooler because it's going to get the cold, the snow is going to absorb the heat from this, so it's going to get colder. But if my water bottle is in here with me in the nice warm room, it's not going to feel the effect of the snow, hopefully. That's because the snow is kind of out there. They're not connected, they're not touching. So in the early universe, when things were close together, they could exchange information. They could pass things around. So by being closer together, by being what we call in causal contact, they could affect each other. So it's not like this particle here is affecting the one that's all the way over there. So this one here affects its neighbor, and its neighbor affects its neighbor, and you get this kind of chain reaction. And eventually you affect the one that's all the way over there. There's a cool classical example, which unfortunately I don't have at hand here, but if you think of a Newton's cradle, you know, the thing where you have 5 balls hanging and you move one and it swings the other one and it goes back and forth. And it kind of looks like the ones in the middle don't actually move. The ones in the middle do actually feel this effect. What happens is the one that comes down connects to this one here. This one here passes the kinetic energy on, which then passes it on, which then passes it on until the end where there's no one else to pass it on to, so it absorbs all of the energy. So you can think something similar in the early universe. When things are close together, they can pass this energy on. If you try to do a Newton's cradle experiment with the balls really, really far apart, you'd swing one and you probably wouldn't get this domino effect until the end because they're too far apart. So when the universe was super dense in the early universe, it was actually easier to transfer information. It wasn't harder, it was actually easier because this one could pass it on to its neighbor and so on. So I think that's a really cool question, and it is an interesting way to think about it, because you might think if there's a big dense object, it makes it harder for things to get around that. But if we're talking about exchange of energy, exchange of heat, the closer things are, the easier it is for them to talk to each other and to pass on this information. So that is a great question. Following on with great questions, let me just check that I'm going through the stream of questions. So as always, if I miss something, I'm very sorry for that. I will do my best to answer all the questions. But directly after this very good question by Paul about the density, there was a great question by Prath as well. Did inflation begin immediately after the Big Bang, or was there some amount of time between them? And I love this question, because then we get into the fun ambiguity that nobody actually knows how to define when the Big Bang actually is. So usually the Big Bang model itself does not include inflation, which is why I often am careful to say that the hot Big Bang model starts when inflation ends. So you have inflation, potentially. We're not yet sure if inflation actually happens. But let's imagine you have inflation. And then I often say the Big Bang model starts when inflation ends. I'm beginning to see that there's no way we're doing 1 hour stream today, because this is already putting me very much out of breath. One sec. Okay, we're going to go as long as my lungs can, but at some point we are going to have to stop the stream. It's probably not going to be an hour today, as you can all see. I'm 22 minutes in and talking is becoming difficult. But tea will help. Tea always helps. Tea makes everything better. Okay, so there's a fun thing here that it's not completely clear how you define time in the very, very, very early universe. And the reason I say this, you'll see a lot of people say things like inflation lasted a fraction of a second and then everything else happened, then hot Big Bang model takes over. But this is not completely true. This is not a statement we can actually say. The reason for this is because inflation erases the memory of anything that came before. You could have 5 billion years of inflation, or you could have 1 second of inflation. The end result would be the same. The end result of inflation gives us the starting conditions for the hot Big Bang model. So then it's a question of what came first, Big Bang or inflation? And this is a very, very difficult question to answer. I'm just going to look for the standard cosmic history map that you've all seen and that people on the show know has a weird name that I'm not going to repeat. Anytime you see this type of image, you'll see the very first entry is Big Bang, and then you have cosmic inflation. So if you define Big Bang as the origin of the universe, the beginning, then inflation comes after. But why would we do this when we always define the Big Bang model? We say there was not an origin, a Big Bang. It's a theory that tells us how you go from the end of inflation until today, which means that technically the correct ordering is some undetermined amount of inflation and then hot Big Bang cosmology. And then this becomes a problem because often among cosmologists, among scientists, we frequently, without thinking, we know that when we're talking about Big Bang, we mean what came after inflation. But when we talk in the general public, there's this widespread opinion, because of how people have presented things in the past, that the Big Bang is the starting point, so inflation must come after. And then some people kind of take advantage of this. There was a very cool scientific paper a couple of years ago where it had the idea that dark matter could have been created during inflation, which is very cool. So then the press release had the title, the paper does not mention Big Bang at all, but then the press release had the provocative title of, did dark matter come before the Big Bang? And when I read that, I was like, yeah, sure, dark matter could have started in inflation, okay. But then the hype in the media and the way it spiraled was people saying, have we found something that came before the origin of the universe? So I think it's a really, really good question here. So let me just repeat the question. Did inflation begin immediately after the Big Bang, or was there some amount of time in between them? Short answer is we don't know. So inflation deletes the memory of everything that came before. So what I would say is that inflation happened for some undetermined amount of time, if it even happened, which we still don't have unequivocal proof of. Inflation happened for some undetermined amount of time, and at the end of inflation, we start our Big Bang cosmology. As to what came before inflation, that's something that we can't really answer, because inflation just pushes everything outwards. It blows everything up, like not literally, figuratively. And it just pushes everything to a stage where you cannot say anything about what might have come before inflation, which I personally think is extremely cool, because we really just don't know what happened before inflation, and I think that's amazing. So it's a great question of, was it Big Bang inflation and then everything else, or what happened here? And my personal answer, and what I think is becoming the more widespread way of phrasing things, is that you had inflation, and then you have hot Big Bang cosmology. But there is not a specific event that we refer to as the Big Bang. In fact, the name the Big Bang was coined by somebody who was parodying it. Like, what are you saying? There was some Big Bang in the early universe, and yet somehow this name stuck. So, yeah, when we talk about Big Bang, we're not talking about one specific event. We are usually from a physics perspective, or like a cosmology perspective. When we talk about Big Bang, we mean the theory that describes the evolution of the universe. There wasn't this like initial point. There wasn't this thing happening at the beginning. Follow up from Paul here. During inflation, the density might have slowed down time dramatically, but it would be the same for the entire universe. So it would be as if it wasn't slowed at all. Guess what you're saying here is that relativity is relative, and I agree. So there's a very cool thing that defining how time passes is not an easy feature. Also, our whole definition of time is completely arbitrary. But let's say we've agreed on some definition that, time moves forward at a rate of 1 second, so on, 1 second per second. What about, we know that if you travel at the speed of light, things slow down. We know that if you're close to a big black hole, that time slows down for you. So how did time behave in the very, very early universe? It's a very good question. Like, if you could follow a photon before the time of the CMB, how would time pass for that photon? And then you can ask the fun question: if a photon travels at the speed of light, would a photon even experience time? Does time have a meaning for a photon? Then we get into philosophical questions, which are very fun. Like, if you travel at the speed of light, time would, which you can't do because you have mass. But hypothetically, if we could travel at the speed of light, we would stop experiencing time, which is very fun and confusing to think about. So the question that it wasn't even a question, it was a comment. I love the more comment than a question. Don't worry, Paul, I'm kidding. So during inflation, the density might have slowed down time dramatically. Yeah, particles there would have experienced time differently to other particles. But this is why we define what we call the comoving time. And the comoving time is a time that moves according to the expansion of the universe. So basically, you put someone or something that is subject to the expansion of the universe, it's feeling this expansion, and you define time based on what this observer would feel. And this is what we call the comoving time, and this is what we generally use in cosmology, because then our frame of reference is the expansion of the universe itself, because otherwise it gets really difficult. So often when we say like the universe is 13.82 billion years old, that's not like from Earth's point of view, that's from comoving time. So an observer who has been around since the Big Bang and traveling with the expansion of the universe would have experienced 13.82 billion years of evolution. But yeah, time is relative. And then you get into fun things like the center of the Earth is actually slightly younger than the surface of the Earth, which is very, very cool. And I love things like that, just based on how time dilates closer to a gravitational source. So that's very fun. So I love these questions about what is happening during inflation and stuff, because there's so much uncertainty. There's so much we don't know about this. It's just so fun to speculate. Okay, so we went through some questions here. We went through early universe, super dense. We discussed. So this is all from the question of what's my favorite theory, and then just follow-up questions. Did inflation begin after the Big Bang? We covered that one. We did if the Big Bang was hot, how did dark matter get cold? Okay. Question from James. As the universe expands, what will the universe percent chart dark energy matter change? This is a really cool question. So let me just bring up the chart in question. And I guess this question came at the time when I was talking about the ingredients of the universe. This is not the image I want. I went too far, but hey, you get another CMB. This is what the universe looks like currently. So currently there is 5% normal matter, 26% dark matter, and 69% dark energy. However, this is not what this chart has always looked like. This chart is today. If you go back to after the end of inflation, what you would get is like basically just photons. You wouldn't have dark matter, you wouldn't have dark energy, because of the way things dominate through different stages of the history of the universe. So different species dilute through the universe at different rates. So when we're talking in math speak, what we say is like radiation goes away as the scale factor to the -4, and then matter goes away like the scale factor to the -3, and so on. And what this just means is how quickly things dilute in the universe, how they travel throughout the universe. And this also gives you a clear evolution throughout the history of the universe. So in the early universe, there was a lot more radiation. Radiation dominates everything. When the first particles could annihilate, you had particle, antiparticle, they smash together, they produce photons, particles of light, which today make up the CMB. But in the early universe, very early universe, you basically just had radiation everywhere. But radiation dilutes away a lot quicker. So if you imagine in the early universe, you have a small amount of dark matter, small amount of dark energy, and a lot of radiation. As the universe expands, the radiation is going to dilute away. And as it dilutes away, you look at what's left, and the next thing you find is dark matter. So then you enter what is called matter-dominated era, where matter is there, and it's the dominant contribution, and then you get galaxies forming, and you and you get stars, and you get structures, and you get everything that makes the universe look so cool today. But then matter also dilutes as the universe continues to expand. And once you've diluted these things away, what is left behind everything else is going to be dark energy. And now we're in the dark energy dominated phase, which is why we're now undergoing accelerated expansion. The universe is expanding. And let me just go back to the chart whose name I'm not going to mention, the history of the universe chart. In fact, let's go to this one, because I think this one shows it a bit better. I have two different versions here. You see here, again, you have inflation, you have the CMB. So you have this first period, like heading up to the CMB, where radiation dominates. Then you have this whole very long period where matter dominates, and this is where you have development of galaxies, planets, all of this. And then you can see towards the end that this starts going outwards. This starts accelerating. This is when dark energy becomes the dominant contribution. When dark energy takes over and becomes the dominant contribution, then we enter dark energy dominated era, and the accelerated expansion kicks in. So we have this gradual progression of things changing throughout the history of the universe. So the question was, how is the pie chart going to change in the future? So that's this pie chart here. So we know that matter dilutes away faster than dark energy. So if we fast forward the universe, what is going to happen is the dark energy contribution is going to grow, the dark matter and normal matter contributions are going to shrink, because the matter can dilute away, especially when the universe starts undergoing this accelerated expansion like it is now. So then it's going to be a battle of structures pulling stuff together, dark energy pushing stuff outwards. So as we progress, the dark energy is probably going to become more dominant, but this is quite hard to determine. And then maybe if we did this pie chart 5 billion years from now, it would look completely different, because maybe there's another component that we haven't realized yet that's hiding behind the dark energy. It would seem quite unlikely, because by now we think we have a pretty good idea of what the universe is made of, but we might be wrong. So the question was, how are these going to change in the future? And it very much depends on the nature of dark energy, which we don't yet know. But the most likely thing, based on what we've been able to see so far, is that dark energy percentage is going to grow and the matter percentage is going to go down, both for normal matter and for dark matter. So those were all some very, very, very cool questions there. And I loved all of those questions, and I love that we could tie them all together. And there's still one more from Scott that I'm going to answer, and then I'm going to go back to stars and black holes that came earlier, but I got distracted on this other tangent, this long tangent. So comment from Scott here, when I was talking about dark matter in the early universe being hotter and colder today, There's a comment from Scott. I just assumed since it doesn't interact electromagnetically, it couldn't exchange heat. This is a great observation. The thing is, we know that today dark matter doesn't interact electromagnetically. Today, dark matter doesn't have weak interactions with the standard model, for an example. Weak interactions would also let particles exchange energy and therefore exchange heat and exchange temperature and exchange information. But it might be that in the very, very, very early universe, dark matter had weak interactions with the standard model. This is, in fact, the most common hypothesis or common model for dark matter. So real estate matter more valuable in future, maybe. Yeah, I'm not sure if we can use cosmology to protect the housing market, but it would be fun if we could. It would be useful, an actual useful application, different type of inflation. So, yes. The most prevalent theory or model for dark matter is what is known as WIMPs, weakly interacting massive particle, as the name implies. These are massive particles that have weak interactions, weakly interacting massive particle, excellent naming convention. This is how we get WIMPs. And the competing idea is machos, because WIMPs, machos, physicists great at naming things, and machos are massively compact halo objects. They just wanted the counterpart to WIMPs, machos. Physicists do not let us name things. So the idea behind WIMPs, weakly interacting massive particles, is that in the very, very, very early universe, dark matter could be talking to the standard model particles via the weak force. Let me just recap again. There are 4 forces in the universe. The one we're most used to is gravity. I drop pen falls down. We stay in orbit around the sun. The sun is part of a galaxy structure. All of this is held together with gravity. Second force is the electromagnetic one. I turn on a light. We can see, I hold a magnet up, I can attract other things. We're used to electricity and magnetism. The third force is the weak nuclear force, which is the one responsible for radioactive decay and for particles talking to each other in the early universe. And the strong force is responsible for gluing things together. It's what keeps quarks together inside protons and neutrons. It's what keeps neutrons and protons together inside atoms. It glues things together. Out of these 4 forces, there are 3 we understand pretty well. And despite my mumble radioactive decay, weak force is one we understand well. We understand strong force, we understand electromagnetic force. We have no idea what gravity's up to, which you'd think is the one we'd understand the most, but it's not. But 4 forces. So in the early universe, there were a lot more weak interactions because it was more energetically favorable. In fact, in the very early universe, the weak force and the electromagnetic forces were combined into what is known as the electroweak force. At some point, these broke apart, and you separated electromagnetic force and weak force. But dark matter might, if we believe WIMPs to be the dark matter, then dark matter would have had weak interactions. It would have been what we call weakly coupled to the standard model. So what we mean by this is that it talks to the standard model particles via weak interactions. And in this case, it's not electromagnetic interactions, it's weak ones, and it would still be able to exchange energy and information with other particles in the early universe. And then this is not, one nice idea about this is that then when the universe gradually cools down, the weak interactions become less efficient. When they become less efficient, the dark matter falls out and it breaks away. And this would be the dark matter decoupling. One thing that is nice, and one of the reasons that WIMPs are so popular, is if you take everything we know about weak interactions and everything we know about the early universe and the energies and the temperatures, and you just imagine a particle that does this, that interacts weakly and then falls away, and you calculate how much of that would still be alive today, you actually find the right amount of dark matter. And this is what is known as the WIMP miracle, the miracle of WIMPs, because you can kind of naturally explain why we have 26.2% dark matter today. Unfortunately, we expected to find WIMPs in particle physics experiments, and we haven't done yet, which means the WIMP paradigm is interesting, but might not work. So, WIMP paradigm is the idea that dark matter interacted very weakly with other particles in the very early universe, and then gradually broke away. However, we have not yet found WIMPs, but there's a lot of ways you can try to save WIMPs. There's a lot of different ways you can change the model to try to make WIMPs so viable, even though we haven't seen them in particle colliders. So that's very cool, because it's a dark matter model that kind of makes sense. Unfortunately, it just doesn't seem to be the solution. Although, of course, I'm going to say that because a lot of my research is asking the question of, okay, if not WIMPs, what else? So I kind of rely on it not being WIMPs. If we find WIMPs, a lot of my papers will be like, well, this makes no sense anymore. WIMPs are nice, not my preferred dark matter model. And my grant applications, which I'm still doing. I feel like every stream I'm complaining about grant applications. Guess what? I'm still doing grant applications. I have one due in 3 days, but it's mostly done. It's fine. And my grant applications start with, we're not going to find WIMPs, so let's move on. Give me money to find a non-WIMP dark matter. So of course, if tomorrow we find WIMPs, I'm going to be a bit disappointed, but it would be very cool. Would you consider recommending books on cosmology? I need to refresh my library. That is a great question. So years ago, I actually, in the very early days of Cup of Cosmology, there was a blog. The blog, I am terrible at updating blogs. The last blog entry was in 2016, so it is not a reliable blog. But as part of this blog, and the original Blogspot webpage of Cup of Cosmology, which you can still find out there, I had a book list, and I recommended cosmology books. Then at some point, I stopped updating the list, and then I realized that my list was very heavily skewed to a specific demographic. Like most of the authors were white men, which is a prevalent thing when finding physics books. So I actually want to make a list of cosmology books with actually diverse authors, and I just haven't got round to doing it. So there's a bunch of books that I think are great for science outreach. There's a bunch of books that I think are good to learn specific topics, but I don't have a list, and I'm not going to do the list off the top of my head because I would forget very important references. But feel free to message me if you have like specific things about cosmology you want to go back to. Feel free to message me and I can send a recommendation your way, because I think there's a lot of great books out there. I just haven't had time to do an up-to-date list, and I actually hid the previous list. If you find my old blogspot, it's easy to find. It's blogspot.cupofcosmology.com. There you'll find the old blog posts, maybe my brain teaser competition that I hosted years ago. But the book list, I think, has disappeared because I decided it's not up to date enough to keep it it's not relevant anymore. But if you want specific recommendations, you can email me, contact@cupofcosmology.com, or ping me on Mastodon, dchooper91_Cosmo. I'm dchooper91 everywhere, except my webpage, which is dchooper. And the amount of times I mistype my own webpage, because literally everywhere else, I'm dchooper91 except my own webpage. But yes, Mastodon, dchooper91_Cosmo. Feel free to message me there or send me an email, and I can send specific book recommendations your way. And as Paul is saying to everybody watching on YouTube, please do thumbs up, click the like button, leave a comment, subscribe, all of the usual stuff, especially now that I'm not going to be sending my streams out to Twitter. It's even more important for me to build up the audience on YouTube. If you're still watching on Twitter, it's quite ironic because for the last 6 months, any of you watching on Twitter, if you put comments, if you like reply to my Twitter post, I didn't see them in Restream. And literally this week, Restream has fixed this. Wasn't on Restream's end. It's because Twitter killed their APIs. But literally this week it's been fixed, and I could now actually see all of the Twitter comments. So if you're on Twitter, you can comment. But as I said before, this is the last week this stream is going to be on Twitter. So too late. So please do all the usual YouTube stuff, all of the interacting stuff, share the stream, everything. It really does help. It really, really does help boost engagement. I don't think you will realize how much it helps. Like if you like a video, the YouTube algorithm is like, someone like this, I should show it to more people, and then more people come in. So please do click all those buttons. Okay, so now I can go back to the question that came in very, very early on in the stream. Where was it? The question by Ben. Sorry, Ben, for ignoring you for 40 minutes. The question had 2 parts. The first one was, is it true that every star has a black hole at its center? What would be the implications? And the follow-up, I should ask if it's possible for stars to have tiny black holes at its center. So there is we know that there is a black hole at the center of every galaxy. So a galaxy, big cluster of stars, there is a black hole at the center. There's a fun kind of chicken and egg question as to what came first, the black hole or the galaxy. We're not completely sure. It depends on who you ask. But as to can there be a black hole at the center of every star? Now, that is an interesting question. So we know that stars are very, very dense. So a star is a constant battle of gravity pulling things inwards and the pressure created by the fusion reactions pushing things outwards. So you have pressure going in, not fusion. Fusion, fission. Yes, fusion. Center of the star is fusion. Yes, we fuse things together. Like Vegeta and Goku doing the fuse. Yes, we fuse things together. This is literally how I remember the difference between fusion and fission. You fuse things together like Vegeta and Goku. Ignore my Son Goku anime references there. So stars fuse things together. So you have a constant battle between gravity pulling things inwards and the pressure of the fusion reactions pushing things outwards. It's this constant battle. If stars get big enough or the fusion stops, like all the stars, this is when you can have fun things like a star collapsing and then exploding. So could there be a black hole at the center of every star? I'm not sure. I think if you had a black hole at the center of a star, then it would disrupt this balance and the star would collapse. But I know there are some models where you can have a black hole at the center of a star, but it is not necessarily every star. I think there needs to be a lot of conditions fulfilled for this. So I would say that in principle, no, stars don't have black holes at the center, but I haven't read the latest literature on this because this is not my topic. There is a thing that you can produce black holes from stars. So as I mentioned, you have this battle, you have pressure, so you have pressure going outwards, you have gravity coming inwards. As stars get older and older, they burn up all of the hydrogen, they burn up the helium, they gradually make heavier and heavier elements. Then at some point, they run out of things to burn. Once they run out of things to burn, they're going to gradually grow because the pressure is going to be so much it's going to push things outwards as it burns up the remnants. But then once it's ran out of fuel, gravity wins, and gravity is going to pull everything back towards itself. Now, when this happens, depending on how much mass you have, you can produce several different outcomes. If it's light enough, relatively speaking, you'll produce a white dwarf. A white dwarf is a star that's reached the end of its lifetime. It's got an afterglow to it, but it's gradually dying. It's a dying star. Next category, if it's slightly more massive, then you would get a neutron star. So a neutron star is a star that is so dense that you can fuse protons and electrons together to make neutrons, and you need a ridiculous density for that. And in a minute, I'm going to tell you a fun fact about neutron stars. And then you could have black holes. So if the star is massive enough, once it's done this whole growing and then collapsing thing, what's left behind would be a black hole. And this is the standard picture for how most black holes are produced. So you get a star reaches the end of its lifetime, collapses, then you have a black hole left over. However, then we have fun things like supermassive black holes. So when stars do this, you expect the black hole left behind to be anywhere between 3 times the mass of the sun and 100, 200, 300 times the mass of the sun, maybe, depending on how big the star is, maybe even 1,000 if you're generous. But then we have these supermassive black holes at the center of every galaxy, which are billions of times the mass of the sun. The most massive one we found is literally 70 billion times the mass of the sun. We have no idea how these supermassive black holes form. Some ideas are that you have a lot of black holes that smash together and eventually grow and grow and grow, and you end up with these mammoth black holes. But another hypothesis, as Scott just mentioned here and tying into the question, is that stars with black holes in the center could have been possible in the early universe and could explain supermassive black holes today. So if the first stars formed already with a black hole at the center, then they would be much more massive than our models currently predict. So then you'd have a black hole and then you have fusion going on around it. And when this happens, then this will collapse and make the black hole bigger. So this could explain this kind of growing black hole chain reaction could explain supermassive black holes. So the question was, do stars have black holes at the center? I would say in principle, no. But some caveats do apply, and there could have been stars in the early universe that had black holes at the center, and there's a lot of work being done to figure out what is happening at the center of stars. But I think in general, I would say that most stars today don't have black holes at the center, but they have the potential to become a black hole if they're massive enough. I am out of tea. I will switch back to water. Okay, so I just wanted to make a fun comment about neutron stars. So neutron stars are weird, right? We know that you have protons, you have electrons. Putting these together requires a ridiculous amount of energy because you need to overcome the electromagnetic repulsion between them. So being able to force these together to actually create neutrons requires a ridiculous amount of energy. And then there's a fun thing that inside neutron stars, matter behaves in weird ways because you're kind of breaking down the bonds, you're breaking down you're throwing out the rule book. So neutron stars are really, really, really bizarre. But neutron stars have the fun thing that the matter inside could undergo what is known as a phase transition. Phase transition is what you get when you boil water and you go from having water to having vapor. Or when you can do the very fun thing and take boiling water and throw it in the snow if it's below like minus 40 degrees and it immediately freezes. That's also a phase transition. And that is very, very cool. And that's about supercooling and superheating phase transitions. And I love the science behind that. I'm not going to do it now, but I will talk about that at some point. But the reason I think this is very cool, in the very early universe, there might have also been phase transitions. I mentioned before, now is when I get to tie the whole stream together. So I mentioned before that at some point the weak force and the electromagnetic force were joined, and at some point they broke away. So when this happened, it might have triggered a phase transition in the universe. The way they separated might have triggered a phase transition. It doesn't within our standard models of cosmology, but it does in a lot of fun models. And the reason this is cool is because these phase transitions in the early universe could produce gravitational waves, which we might be able to see within the next few decades. And that's what I'm working on now. I used to work on the CMB and dark matter, I still do. But now I'm trying to figure out how we can use these very early universe phase transitions, the gravitational waves they produce to study the first second of the universe. It's amazing. What's this got to do with neutron stars? Well, the physics we use to study early universe phase transitions and the physics being used to study phase transitions inside neutron stars has a lot of overlap, to the point that in Helsinki, there's a lot of people working on phase transitions in the early universe, like me and my colleagues. And there's a lot of people in our group working on phase transitions inside neutron stars. And there's a surprising amount of overlap in the physics, in the language we use. Now, the type of phase transition is different. The energy scales are different. The physics is different, but the mathematical description is surprisingly similar. And this is really cool because then I go to seminars about neutron stars. I'm like, why am I in a seminar about neutron stars? And then they talk about phase transitions. I'm like, hey, I understood that, and vice versa. So this was just a random way to plug in my own research here, but I think it's really cool that in neutron stars, you can have kind of the same physical process, much different, but at its essence, a phase transition. You can have this in neutron stars, you can have this in water bubbling, you can have this in early universe physics. And that is very cool. And I think nobody asked, but I'm going to mention it anyway. I think one of the most important subjects that we learn as an undergrad in doing your bachelor's, your undergrad in physics, is actually thermodynamics. Thermodynamics and statistical physics. And I say this as somebody who hated that course at the time and who did badly in that course, partly because I was taught that course in German without actually speaking German, which was fun. But it did teach me German. I learned fun words like Geschwindigkeit, which means speed. I hate that word. So that was literally one of my first German words, tangents. So I think thermodynamics is really cool because you learn about these phase transitions, you learn about energy transfer, you learn about entropy. And then at some point you realize that literally everything in the universe is related to these things, which is kind of cool. So Geschwindigkeit, yes, it's almost like you're sneezing and someone's like Gesundheit, Geschwindigkeit. Yes, Geschwindigkeit, fun word. And I at some point had to learn the word for like the probability distribution of velocities, which I do not remember anymore, but it started with Wahrscheinlichkeit and ended with Geschwindigkeit, and I was like, what the no. Welcome to German. It was fun. So yeah, I think thermodynamics is a great course because you learn about all the cool physics that then explains water bubbling, neutron stars, and potentially the production of gravitational waves in the early universe. Is amazing. It's amazing. Comment here by Paul. There's a cool 1980 science fiction book called Dragon's Egg by Robert Forward about a civilization that evolved on a neutron star. That seems very cool, actually. I'd like to see how they go about having a civilization on such a star. Would be very cool. Steam tables are the main thing I remember from that course. Yeah. And doing like diagrams where you show the phase transitions and like phase diagrams. I used to hate those. You know, picking apart all of the statistical thing there. But now I'm like, hey, I remember studying this. I think I probably would have enjoyed the course a lot more in a much different context, but it's a really important course and probably the one that I actually come back to the most now, which is surprising. It's not cosmology, it's thermodynamics. Although my cosmology course was also great. German and Japanese love making gigantic compound words. Have you heard of Finnish? because Finnish does this too. Finnish takes 500 words and smashes them together, and suddenly you have a monster word with 50 consonants back to back. Good luck pronouncing that. And people are like, just pronounce exactly what you see. Like, I'm going to run out of breath halfway through this word. There are Finnish words that are... I had to do a fun thing for my grant proposal, the one that is due in 3 days. I have to write a public description of the project in English and then translate it in Finnish. Now, obviously, for the Finnish translation, I just pester my colleagues like, hey, can you translate this for me? But there's a fun thing that there's a word count, there's a character count, and the character count is the same in English and in Finnish. So what I've learned to do is like give myself 100 characters margin in English, because I know the Finnish translation is going to eat up all those characters. So I have a 1,000 character limit. This time my English version is like 920, and my Finnish version, the one that my colleagues translated for me, is like 992. So all those characters just going through words that were spreading. So yeah, German, Japanese love making gigantic compound words. So does Finnish. I love Finnish language. It's a very cool language. Someday maybe I'll actually learn how to speak it properly. But that was just a random rant there about Finnish words. Okay, 56 minutes in. I think that went better than I expected. Sorry to everybody for the random coughing fits. I did anticipate it would still be a bit tough today, and this is why I didn't do a stream last week. But I managed better than I expected, so that's good. And I think I got through all of the questions. You all had some really, really cool questions today, and I like that. A lot of the questions were connected, and I kind of just went through the history of the universe and cool things, and we talked about WIMPs and neutron stars. So it's really cool. Thank you for all the cool questions. It's been really fun. It's great to come back. Every time I take a break from Cup of Cosmology, I honestly think, like, do I want to go back? You know, I'm on a break. There's that inertia. And then I come back and you all have amazing questions and it's engaging and it's fun. And I'm like, I love this so much. Why would I ever stop? So thank you for keeping me coming back to Cup of Cosmology. And thank you for coming back to Cup of Cosmology over 8 years now. The first stream was the 13th of August 2015. So it's been over 8 years, and some of you have been here since the beginning. I know there are some of you who've been following me for 6, 7, 8 years, and it's amazing to me that you're still coming back. Thank you. Thank you for that. It's great to see so many of you here. I really am always very happy to see so many of you come here and ask me questions and have these conversations with me. It's so much fun. Thanks for doing the broadcast. Welcome to. I'm happy to be here. Sorry to hear you're sick, Scott. Hope you get better soon. And as you're saying, Paul, you hope I start feeling better quickly. Honestly, I'm feeling much, much, much better than I was 2-3 weeks ago. So my COVID, I actually ended up in hospital with COVID. I spent Christmas Day in hospital because of COVID. So the way you see me today is a lot better than I was 3 weeks ago. I've got lingering effects, but they're clearing. And my long COVID, hopefully someday will get better. So don't worry about me. I'm getting better. I am recovering. Cup of Cosmology should be back online next Sunday. Do I have anything next Sunday? Let me check my calendar, because somehow a lot of events have just appeared in my calendar recently. I don't know how this happens, but like last year I traveled and I did too much and I did too many things. And I told myself that this year I would do fewer things, and yet somehow my calendar is full. I've already agreed to 5 talks this year, and I've already agreed to like 3 or 4 travel 5 trips maybe. So my calendar is just getting full and full and full. And I just opened my calendar and realized I'm giving a talk in 2.5 weeks. For those of you in the past who have seen iTelescope talks, the iTelescope network is amazing, and they have weekly seminars on Fridays about really cool topics covering every aspect of space. If you go to iTelescope.net, you'll find the seminars. I will be giving another iTelescope seminar. I've given 3. I'll be giving a 4th one on February the 2nd. It will be a 1-hour conversation about a topic that I haven't yet figured out, but it's going to be fun. So I'll post links on Mastodon to that, so feel free to follow me over on Mastodon. As I mentioned before, this is the last stream on Twitter. Make sure you all head over to YouTube, click the subscribe button, click the notification button so you'll get notifications when I go live. Follow me on Mastodon, DCHooper91_Cosmo. If you just go for DCHooper91, you'll find my personal Mastodon account. You can also follow me there, as long as you're prepared for a lot of queer rambling and just random stuff. But then you can also link to my science one. Okay, thank you everyone for joining. As I said, this has been really, really fun. It's been great to see everybody here. It's been great to have all of your questions and chat to everybody again. I'm going to go rest my voice. Cup of Cosmology should be online again next Sunday, same time as always. I hope to see you all then, and I hope in the meantime you'll stay safe and take care of each other.